In this section, we're going to talk about comparison tests, where we are comparing one series to another to determine if it is converging or diverging. So we're actually going to have two tests, but to differentiate the two, I'm going to go ahead and call this one, rather than just saying comparison test, I'm going to go ahead and add in this word direct, the direct comparison test. So the test we're going to call the comparison test. We can use CT for short, or DCT for direct comparison test. And we're going to take two series, and they do have to have positive terms. So for this comparison test, we do need to be looking at series that have only positive terms. So a sub k and b sub k are greater than or equal to 0. Then, if all the terms in a sub k are less than or equal to all the terms in b sub k, and b sub k converges, then a sub k must also converge. Okay, so what are we saying right there? Well, a sub k terms are always smaller than b sub k. So I think of the a sub k series as the smaller series, b sub k as the larger series. If the larger series that is essentially smashing a sub k underneath it, because a sub k is always smaller, if b sub k is converging, then it should follow that a sub k must also converge. And the condition for divergence for the direct comparison test says this. Same inequality, a sub k is the smaller, a sub k terms are always less than or equal to b sub k terms. Then if a sub k, if this series where the terms are smaller than the other series is diverging, then of course b sub k must also diverge. So it, hopefully intuitively it makes sense. We're looking at two series where one is always smaller than the other. If the smaller is diverging, let me get my cursor in the right spot. If the smaller is diverging, then the larger must also diverge. But if the larger is converging, then the smaller must also converge. Okay, just a couple of comments. When we are working with the comparison test in general, especially the direct comparison test, you have to first find a series that you can easily compare to. And the ones that we know right now that would be easy to compare to are the geometric and the p series. So those are good ones to think about. So let's go ahead and look at a couple examples. Okay, so here we go. So we've got the series from k equals 1 to infinity of 1 over 3 to the k plus k. Now, up here above this, I want to just mention a couple of little notes about using the comparison test. Now, we've only considered the direct comparison test, but we're also going to have a comparison test called the limit comparison test. So the first thing, doesn't matter which of the two comparison tests we're working with, the first thing that we have to do is we have to determine the series we want to use to compare. So determine the series to be used to compare. Now, this is, and I mentioned this in the comments on the first image that I had projected, but this is where we might want to think about our P series. We might want to think about, does it look like a P series? So think about the P series, right? Does it look like 1 over K to the P? Or the geometric series? Does it look like A times R to the, let's say K, R to the K? Does it look like one of those? Or some other known series? So that's the first thing that we have to think about. We have to think about, does it look like something we know converges or diverges essentially by inspection, which we can see from the P series and the geometric series. We can normally pretty quickly determine if those two are converging or diverging. So that's the first thing we do. The second thing that we do is we then apply direct comparison test, or what is called the limit comparison test. Now, to use the direct comparison test, which is what we're going to do on this video, to use the direct comparison test, we have to be able, so we use this if we can easily build the inequality. So remember, in direct comparison tests, we need a sub k less than or equal to b sub k for all k greater than or equal to n. So I won't go back to the image before, but we have to be able to create an inequality where all the terms a sub k are less than b sub k, and then compare. Okay, so that's what we're going to have to do in order to use the comparison test. So let's take a look at that in the context of an example. So on this particular one, the first thing I have to do is I have to figure out what do I want to compare it to. So I'm looking at this, I got 1 over 3 to the k plus k. So I'm looking at that denominator. Obviously, the numerator is just that constant 1. But in the denominator, I've got an exponential term, 3 to the k, and I have a linear term. So this exponential term is going to dominate. This is what I'm thinking. This exponential term dominates. This gets much larger than the k term. So this exponential term is going to dominate the denominator. So that's giving me an idea of what to compare to. And I'm thinking, what if we compared to 1 over 3 to the k? Because essentially that 3 to the k is going to grow much faster than the k. You could also think about growth rates of those two terms. So 1 over 3 to the k is a geometric series, because that's 1/3 to the k. And that is a geometric series, and in that geometric series, the common ratio is 1/3, which is less than 1. So that guy converges. Okay, so that's the start. That gives me a place to start. It gives me something. So remember, we have to start by figuring out what is it we want to compare to. And once we've done that, I guess I took it a little further. I also stated that it's going to be converging. So that's what I want to compare it to. Now, the next thing I need to do is I need to build, if I can, I need to build the inequality. So we compared, figured out what it is we wanted to compare to, and now we want to build the inequality. So I'm thinking here, okay, so I want to compare to 1/3 to the k, or 1 over 3 to the k. So I'm going to start this way. I'm going to start by saying, well, the denominator, 3 to the k plus k, that's always bigger than just 3 to the k for k values that are greater than or equal to 1. And when I reciprocate that, 1 over 3 to the k plus k then would have to be less than 1 over 3 to the k, which is the same, by the way, as 1/3 to the k. I will write it that way just so we can see it too. So that has to be true. And one other thing, these are all positive terms for k greater than or equal to 1. So we could also say that this guy is greater than 0. There are positive terms is what we're saying right there. These are positive terms. That was the other thing we do need to be careful of. We got to make sure we can't apply a comparison test unless we're working with positive terms. Okay, so that's the inequality. And so we have everything we need. We know that this series 1/3 to the k is converging, and we know that the series of the terms in the series we're looking at are always less than that series. So we've got it. We have everything we need to say, therefore, by the direct comparison test, and that's a direct comparison because I built the inequality, by the direct comparison test, the series I'm looking at, 1 over 3 to the k plus k from k equals 1 to infinity, because that is the smaller series, it is always less than this series, which is larger, but the larger series is converging. So it must, by direct comparison test, this guy must converge since 1 over 3 to the k from k equals 1 to infinity converges by geometric series. Now, these are like little mini proofs. We're showing all of the work here. We're getting it all set up. We showed up above that this converges by geometric series. We set up the inequality, and then we have our nice little conclusion. Then, of course, by direct and stating which test we're using. By direct comparison, the series we're looking at must converge because the series that it is always smaller than is a geometric series, and that is converging. Okay, let's look at another example. Okay, so let's take a look at this guy. We've got k over k squared minus cosine squared of k for the terms of the series from k equals 1 to infinity. Now, very similar to how we thought about on the last one, I'm looking at this denominator, and for one, this is bounded. This term in the denominator is bounded. Cosine squared of k is always less than or equal to 1, and since it's squared, it's always greater than or equal to 0. So this guy is going to grow much. Well, this guy's going to grow without bound, actually. K squared grow without bound. But if you think about the denominator, this is going to be dominated by the k squared term. And as k grows and grows and grows, cosine squared minus k isn't going to make much of an impact on the denominator. So again, remember, we're using the comparison test. And the first thing I have to do is I have to figure out what is it that I want to compare to. So what do I want to compare to? And as I'm thinking about that, I'm kind of thinking about how do each of the terms in the definition of the series pan out. And in this case, that cosine squared of k is essentially going to become obsolete as k is growing and growing and growing. So if I just drop it off and I think about, well, what happens to just k over k squared? Well, k over k squared would be 1 over k, or 1 over k to the first, from k equals 1 to infinity. And that is a p series. It's actually the harmonic series, so you could think of it, or think, we've talked about that harmonic series quite a bit. But the harmonic series is a specific p series where p is equal to 1, and so that guy diverges. So the p series diverges when we're less than or equal to 1. And so you could also have just recognized that it was the harmonic series. You could even have stated that. We have shown that in a previous video. We have shown that that is definitely going to diverge. Okay, so that's going to diverge. The series we want to compare to is going to diverge. So what we want to do is we want to see if we can build the inequality. So let's build the inequality, if we can. Now, if we can't properly build the inequality, then we might want another test, and we'll save that for another video. But let's see if we can build the inequality. So we've got a diverging series. We want to actually be able to show that our series is bigger than this diverging series if we're going to use direct comparison. So let's go ahead and do that. So we're going to start off in the same way. Start off with the bottom. Oh, by the way, these are so from 0, just as a note, these terms, k squared minus cosine squared of k, for k, excuse me, for k greater than or equal to 1, is definitely positive. So these are, again, we do need to make sure we're looking at positive terms, and these are going to be positive terms because, again, we mentioned that bounded piece, and since we're starting at 1, k squared starts out at 1 and continues to grow. Cosine squared of k never gets bigger than 1, so these are definitely going to be positive terms. So k squared minus cosine squared of k is greater than 0, and it is also less than just k squared. So when I flip these, reciprocate them, I get 1 over k squared minus cosine squared of k is going to be greater than 1 over k squared. And if I multiply everything, and I can do that since k is positive, greater than or equal to 1, when I multiply everything by k, I get k, the terms in my series I'm looking at, k over k squared minus cosine squared of k is greater than k over k squared. But k over k squared, of course, just reduces to 1 over k. Now I'm just going to rewrite the inequality. Just flip it around. So 1 over k is less than k over k squared minus cosine squared of k. Now, we already talked about how that was greater than 0. These are positive terms. So I will just add that in. It is important that we do verify before using the comparison test that they are only positive terms. And these are. Okay, so we've got 1 over k. So look at this. The smaller, right, the one that is less than, the terms that are smaller, is diverging, which is going to force the one that is bigger, larger, to also be diverging. So we have everything we need. We're just going to summarize it now in a summary statement. We're going to say, therefore, the series that I'm looking at, k over k squared minus cosine of k from k equals 1 to infinity is diverging, or you could just say diverges. Let's say it that way. Diverges by, this was a direct comparison test. We were able to directly compare in an inequality this guy to 1 over k from k equals 1 to infinity, which diverges by p series, p equals 1, or if you prefer, you could have said that it is the harmonic series, which is diverging. All right. So again, I just wanted to get this all on the screen and zoom in on the notes about the comparison test. Again, with the comparison test, what we want to do first is determine which series we want to use to compare to, and then second, we actually are going to apply the direct comparison test or the limit comparison test. So we talked about applying the direct comparison test if we can easily build the inequality. On the next video, let's talk about what's called the limit comparison test, and that's going to be used when we cannot directly build the inequality, but we still want to compare to a series we know converges or diverges.